Okay, hello. So I'm going to show, just talk through some using of sagemath to draw pictures and compute things. So first, this is a Sage worksheet, so I could go here and I have a folder and these are a bunch of files, and you can click new Sage worksheet and it would open one up. You give it a name and then you can go into it. Here's some other files. There are many other things you can do, but I like the Sage worksheets best. So then you can run a cell by holding shift and pressing enter. So I can also make a new cell up here, and that tells me that A is 3/2. I can print A. I can show A for like a prettier version of it. I can also get rid of that cell entirely and just go back here. Now what else did I do? Well, I just created on this line I created some variables, so I could do that above, like bar x. And now the computer knows about this variable x, so I can make equations, say, out of it. Let's call this GG, because I already called something G down there. And then I could say print GG. I could say take GG and take the derivative. So right there, I did .der, and then I pressed tab, and it automatically filled it in. Because when you create an object and you run a cell, and now computer knows what GG is, now it knows that there are a bunch of things you can do with it. You could take absolute value, coefficients, and you could. So this is a good way to see what you can do. And one of them is derivative, or diff, or differentiate. These are maybe even doing the same thing. So I could click derivative, and if I want to know what happens, first, I mean, if I just run it, I get some weird thing. It's saying that this is actually a function. I need to give it arguments. And so I could say derivative with respect to x, and it takes the derivative here. If I did with respect to y, it'll get the derivative with respect to y. I can get rid of that. So we could also take the gradient with respect to x and y and get the gradient and all these sort of things. If you're wondering, you can press, if your cursor is inside the parentheses and you press tab, then it'll tell you about how to use this function derivative. And it'll tell you about, it'll give you examples of how to use it. And this is a good way to learn a lot about what you can do. And maybe this will help if I zoom in. Okay, so if I put my cursor inside the parentheses and I press tab, it'll tell me. I can get out of here by pressing escape or by clicking on the X button. Anyway, so now I create some variables so that the computer knows what it is, and I put them in a list. Okay, so the computers have, now since I've already run that cell, I can even go up here, and the computer knows what vars is, because you can run these cells in any order. And I put them in there in this list, which you can create a list with these square brackets, because I'm going to use them later. Here I created a function. I'm thinking in my head that g of xy equals 0 gives me the equation of an ellipse. Then to plot the ellipse, I use an implicit plot command. And if I just type that and press tab, now I get some options to complete. Implicit plot 3D is apparently an option. I don't need that. So anyway, so if I run this cell, let's just run these ones. So I'm going to copy and then go up here and just run those. And now what I've done is I've saved it as PLT for plot. And if I actually just type PLT as the last command, it'll display the plot. So here's the implicit plot of this ellipse. Okay. If I want, I can add something to the plot. Like I can add the point like 1.5, 1.5. and that will complain. This is an error, and so it says point takes one positional argument, but two were given, and so maybe I need to put these coordinates in a list. So I do that. Oh, and then I didn't print out the picture, so I have to type that and then press Shift-Enter, and there's my point up there. So this is kind of nice about Sage is you can add pictures to other pictures. Okay, so in fact I could even say like this is plot 2. And now I can display plot 1 plus plot 2, and what will happen is now the point image and the implicit plot of the curve image will be added together, and I'll get a point up in the top right. There it is. Okay, and I can make this point bigger by saying size equals 40. And there's the bigger point. And so anyway, you can add images. So now what I'm going to do, well, first of all, let's just put these all in one line again, or one cell. I'm going to get rid of this stuff I don't need. Oh, one way to get rid of things, you can highlight them and then type Command ? Or maybe Control ? on Windows. I'm on a Mac right now. And the computer will ignore anything on the line with a hashtag in front of it. So like the computer ignores this. This was just for me. This was we call this a comment. And it'll just ignore everything after that. So I can comment these out, or I can uncomment them. Comment, it'll ignore. Uncomment, it'll do it. So I'll ignore it. And now, what am I doing down here? So here's the gradient with respect to the variables. See why it was useful to put them in a list and call them vars, because then I can compute the gradient. Then I created a new variable t. I'm going to parameterize this ellipse. So now p is a vector with 2 entries, so it's like, really, in my mind, this is a map. It sends t to the vector with 2 entries, a times the cosine of t, comma b times the sine of t, and that's a in 2 space. And so that's good. Now I could, of course, do something else. Like I could create a function, like f of t equals a times a times cosine of t, comma b times sine of t. And if I create that function, then I can say what's f of 2, what's f of 3. But I can't really take the derivative as easy. Well, maybe I can. Let's see. Derivative. Oh, so it took 2 derivatives. And well, anyway, so you never know what the computer can do. But instead of doing it as a function, I did it as sort of this vector object. So let's see what little p is. Let's look at little p and say maybe what's type of little p. So it's a Sage module. It's a free module over an ambient field. Okay, so what's the field? Actually, it's a ring, I think. Maybe it's base ring. Yeah, base ring. Okay, so what I'm showing you is that when you create a variable and declare a variable, then there's this new ring called the symbolic ring. And the computer can do addition, division, multiplication, and stuff in this symbolic ring. It can do derivatives. And so that's actually pretty useful, as opposed to a function, which is not computing in the symbolic ring. So like, yeah, functions are not as nice for this. But if I create a vector with variables, then it's a vector over a symbolic ring, and I can do sorts of. So there's sort of 2 things. You can either do the symbolic ring, or you can do functions. And a lot of times, one is better than the other, and you'll learn with experience. So now I create. Okay, so what am I doing? I created this vector p, And now the thing is that now it's not as easy to call like p of 2 or p of 3 like we could do with the function f of 2, f of 3. So rather what you do is you create a dictionary. This is a dictionary. And it gives instructions for how to substitute. It says take the variable t and substitute the number tt. I called it tt because I was going to plug it in for t. I could call it something else. Now what's this S range? Okay, so let's just take this so you can see what this is doing. Print tt. So S range is starts at 0 and ends at 1 and goes by increments of 0.1. And yes, it starts at 0 and ends at 0.9, but whatever. You figure that out when it happens. And so this is just my way of sort of getting a bunch of different numbers, and I'm going to plug them all in. Down here, I create first a dictionary, and then I will substitute the t-subs dictionary in for this symbolic ring vector, which will then become an actual, like, a vector with numbers in it. And then, what am I going to do? Oh, let's comment this out. This is more advanced. And now let's show the plot. So you see what I did is I took those numbers, I plugged them in, and I got a bunch of points on the ellipse. Okay, so this is how I get actual points, is I use the parameterization. If I went longer to 2, and then I show it, I'll get more points. If I go all the way to 2 pi, then I'll get points sort of all around the ellipse. And I could keep going, but I'm not going to. So I'm just going to stop there for now. And now let's say, now what did I do? I took my plot, which I created up here, which originally just had the curve, and then I'm going to add a bunch of points to it. And they're all going to be blue and size 20, and they're the points capital P, where I've substituted in all these different numbers up here. So I'm just plotting. Now, what if I don't want to do that? I want to do something else. So this time, instead of plotting a bunch of points like here, I'm going to do the normal lines. So first I use my gradient up here, and I substitute in at those 2 points. Now here's my xy subs. I'm going to replace x with the first coordinate of this point at that t value, and replace y with the second coordinate. So this p of 1, p of 0 is like, here's this. If I want to just pull out the first element, Python is 0 indexed, so that will give me the first element, whereas the second element looks like that. And if I ask for the third element, it'll give me an error because this vector has only 2 entries. Okay, now capital P is a vector with numbers. And so if I pull out the first number, I get that 0.93. And that's really what I'm doing here, is I'm saying replace x with that number, replace y with that number. And then I get my gradient at the actual point. I go minus the gradient, and I go plus the gradient. These give me 2. That's another reason you can't do this with functions. So right here, I'm doing vector subtraction. Here's vector addition. And it's doing that over the symbolic ring. And it's really important that I originally set this up as a vector. Okay, and I could even specifically say it should be over the symbolic ring, and that would work the same. And okay, that's kind of cool. So I spoiled what we're doing here. Then I plotted a line between these 2 points. I start at P, like let's say that point P, and I go minus and I go plus, and I make the computer draw a line. And at first, actually, when I was doing this, I tried line from A1 to A2, and the computer complained. It said it takes 1 positional argument, but 2 were given. And so I said, oh, maybe they want the points in a list. So I put them in a list. The computer was happy, and I got my lines. Okay. Now this is kind of fun. So let's do this for more points. See, I'm going around, and let's just go all the way around. And maybe we need to go like a little bit longer in the gradient direction in either way. So I'm going to get a little longer lines, see. And let's keep doing this. Let's go all the way to 3. Interesting. So I'm just drawing the normal lines to this ellipse. All these lines are at 90 degrees because the gradient vector is always normal to the curve, to the implicit curve. And let's just keep going. How about to 2 times pi? And now, this is what I really wanted here. This curve that is appearing is called the evolute of the ellipse. It's a new curve. So I start with the ellipse curve, and then I do this construction with these normal lines, and all these normal lines sort of bunch up together at these special points. It's very cool what's happening. So the normal lines over here on this part of the ellipse are bunching up together over here. And let's see, maybe if I do like 1.5, 1.5, just drawing longer lines, maybe you can sort of see how really they're bunching up. It's not just the end, it's not like just the end points matters, but it's more where they're bunching up. So let's even do a longer line. You can still see they're bunching up at this sort of a diamond shape. Okay. And yeah, so they're spreading out. Let's even go to 3. Yeah, now, amazingly, there is a parameterization for this curve. I just wrote it down. I didn't tell you at all how I get it. But now if I add this to the plot, I'm going to plot all these points. You see that I'm actually getting the curve, those red points. Yeah, how come they're not? Maybe I have to make them bigger. Okay, maybe this was too many lines. Here, let's do less lines. Okay, and then that was, but over here I'm going to get all the points. So that's the curve. Maybe that's too large then. Oh, I have to rerun it. Anyway, so I hope this has shown you a little bit of what you can do with vectors and parameterizations and implicit plot. And when you have parametric equations for the curve or the surface, then you can just literally plug in numbers and plot points. There is also a way to do parametric plots like this, where you just give the parametric equations, choose values for the parameter, and it'll automatically plot points for you. So that's a good way to learn, is you go up here and you can find different like parametric curve in 3D. And so here we see a different way to declare a variable u, and then they gave 1, 2, 3 parametric curves, which traces out this helix, and this is how you can plot it. So you should play around with all these different things and see what you can do. Here's a parametric surface. Maybe it's because here, let's get the parametric surface. So here's a parametric surface. I think this is supposed to be some sort of a Klein bottle. And you see some parameters like you can make it spin. And now here the parameters are u and v, and they have to range from 0 to 2 pi. And then we have 3 functions that are defined up here in terms of u and v. And so this sort of takes the uv plane, the 2-dimensional uv plane, and throws it into 3-dimensional space in this particular way. And then we could start trying to get the tangent planes and normal lines and all sorts of stuff. Okay, that's enough for now.